All right, welcome back, everybody. So last time we started talking about orthogonal bases and other ways to represent subspaces. So I want to continue that discussion today. And in particular, let's just start by refreshing our memories of where we were before. Let's start with some matrix X that has n rows and p columns that could correspond, for instance, to p different features that we observe for each of n different samples. And let's write its columns as x1, x2 through xp. Each one of these columns corresponds to one feature for all of the different samples. And then last time we talked about subspaces. So we can let S be the subspace span by the columns of X. And what we talked about last time is that when we use that language, what we mean is the set of all vectors that are the same size as each of the xi. So each one of these is length n. So the subspace is all vectors in Rn that can be written as a weighted sum of the xi's. So that was what the notion that we introduced last time, this notion of a subspace corresponding to everything that can be written as a weighted sum of these xi's. And then we said, let's introduce the notion of a basis. So we could say, let U1, U2, all the way through UR equal orthonormal basis vectors. Orthonormal basis vectors that span this subspace S. So what did we say we meant by that? What we mean is that any vector in this subspace S can also be written as a weighted sum of the UIs. Okay. Now, in this notation, R is equal to the dimension of the subspace, and this is the same thing as the rank of the matrix X, and this is the same thing as the number of linearly independent columns in X. Okay, so the key point here is that for every vector in this subspace, there's multiple ways of expressing it, but in particular, we could represent it as a weighted sum of the xi's or as a weighted sum of the ui's. So imagine that we come up with some predictor of labels, y hat, that we can write as xw. Then for any w that we choose, or for any y hat that has this form, we can also write y hat as u times, let's say, w tilde, for some w tilde. So we can always write y hat in this subspace either as x times one weight vector w, or as u times some other weight vector w tilde, where u is the basis matrix. So it'd be u1 vector concatenated with u2 vector all the way to the ur vector. So this is a matrix that's n by r. And we said last time that this notion of an orthonormal basis was helpful when it comes to computation. So in particular, because these ui's are orthonormal, then that implies if I were to take the inner product of ui and uj, what does that inner product have to be? Yeah. Okay, so I heard the word identity, and yes, that's exactly where we're headed. So it's either a 1 if I is equal to j, or 0 if I is not equal to j. And what this implies is if I take the whole matrix U times the transpose times the matrix U, then each element of this product has this form, and so this product is equal to the identity matrix. And in general, it's not always true that U transpose is equal to I. So there are some special cases where that is true, but you can't count on it. Oh, I'm sorry. Yeah. Sorry. Okay. No problem. Is the first part usable still, you think?
Yeah. Oh, yeah. Wait.
Great. Okay, so this was a point of confusion after last week's last lecture. So this orthonormality assumption implies that U transpose U is equal to the identity matrix, but U could certainly be a rectangular matrix, and so U transpose may not be the identity matrix. Okay, so now what we said last time is that we can use this setup in the context of least squares. So in particular, we said, well, if we wanted to find W, then we would search over all possible weight vectors and choose the one that minimizes the distance between some true label vector and our predicted labels x, w. Like that, and we said, well, if the columns of x were linearly independent, then this would have the form x transpose x inverse x transpose times y. We can also use the same kind of idea to come up with w tilde. So again, we can say, well, what's the weight vector that minimizes the distance between y and uw? And using the exact same logic, we can say, well, this is going to look like u transpose u inverse u transpose times y. So why would we care about this instead of this? Yeah. Right. U transpose u is the identity, and of course the identity inverse is still the identity. And so this is simply equal to u transpose y. So in your homework, you are working with this problem with people's bases and different features for that. So the size of x was, I think, 128 by 9. So this x transpose x matrix is 9 by 9, and inverting it is no big deal. If I were instead working with the ratings collected by Netflix, then x could be, say, 5,000 for the number of movies by 100 million. Wait, I said that wrong. Well, 100 million customers. So now all of a sudden x transpose x is 100 million by 100 million, and inverting that matrix is much more problematic, right? And so what we see is that if we've got an orthonormal basis, there are some problems that we can solve very directly and very easily with much less computation than this more naive formulation would require. But then the question becomes, and this is the question we never really answered last time, how do we get U? Where is this orthonormal basis coming from? If we had it, we know something about how we might use it. There are ways we can use it even beyond what I've written here so far. But how do we even get U in the first place? So today I'm going to talk about two different approaches. The first is Graham-Schmidt orthogonalization. And the second one is the singular value decomposition. So we're definitely going to get through Gram-Schmidt today. We're going to start to touch on the SVD. This is the SVD. And on Wednesday, we'll really flesh out the ideas behind the SVD, which is an extremely powerful tool used throughout machine learning. And what you're going to see is throughout all of this, we continuously use least squares estimation and orthonormality of bases. So these concepts and tools that we've been developing all quarter are going to come into play in major ways for both of these topics. So the name of the game is taking a matrix X and finding a basis matrix U. Any questions so far? Okay, so with Gram-Schmidt orthogonalization, what we're going to do is start by just looking at a couple of very simple toy examples, and then we'll talk in more generality about how you would actually do this. Okay, so let's have the first column of x, x1, be equal to 2, 0, and the second column, x2, be equal to AB for some numbers A and B. We're going to talk about how Gram-Schmidt orthogonalization changes for different values of A and B. But for now, just think about them as some generic constants. So we can draw this pictorially here. So I've got my first and second axes, and I can put my points on them. So here's 1, and here's 2. So here is x1. And then let's just imagine that this is A and this is B. And so here I've got x2. Okay, so I've got two vectors. They are not unit length, and they're definitely not orthogonal. They're not at right angles to each other. So what we want to do is we want to take these two vectors and find an orthonormal basis. So first of all, just as a little warm-up exercise, what is the span of these two vectors? So what vector?
The diagram, they're not linearly dependent, so they'll span all of R2.
That's exactly right. So they are not linearly dependent, and therefore they span all of R2. So any point in this whole plane, here or wherever else you want to be, I can write as a weighted sum of x1 and x2. Okay, so what we're really going to learn when we learn a basis that spans the same space as these x's, we're going to learn a basis for R2, the two-dimensional plane. Okay, so the way Gram-Schmidt orthogonalization is going to work is we first take the first column, x1, and then we make it unit length. We divide by its length. And we're just going to call that u1. So our first vector in this basis is going to be pointing in the same direction as x1, but it's going to be length 1. So this is u1, 1. Okay, so that part was simple. Now what we want to do is we want to find another vector, u2, that's going to be orthogonal u1, also unit length, that's going to capture everything that's in x2 that wasn't already captured by x1. So in particular, what we're going to do is we are going to write x2 as being equal to a weighted u1 plus some sort of residual. So we're going to try to represent as much of x2 as possible using u1, and then some residual that represents everything else. Okay, so in particular, we can write x2 as being, so u1 now was, oh, sorry, we didn't do that. So x1 is equal to 2, 0, and the length of x1 is what in this case?
2.
2. And so u1 is just 1, 0, which is what I drew on the board over there. Okay, so now we're going to write x2 as some weight here that we're going to figure out times this u1 vector plus something else. So what we want to do is we want to figure out what these question marks should be. And in particular, we want to make this question mark be such that we're representing as much of x2 as possible using u1. So any thoughts on what this should be? I know I'm not stating things super formally yet. We're just going to build up to that. A, exactly right. So the first thing, so we write this is A, and then what's in our residual? What's left now that has in x2 that hasn't been represented by A times u1? 0 and B. That's right. So what we're going to do is we're going to call this residual x2 prime. So it's x2 minus everything that we could already represent using u1. So A times u1. And now to make u2 our second basis vector, we're just going to take this x2 prime, this residual, and divide by its length. So the residual vector we said was 0b, and what's the length of that vector?
B.
B. And so we're left with 0, 1. And that is our second basis vector, and if we draw it on our plot, then it just looks like this. That's u2. And so you can see these two vectors are both unit length. They are orthogonal to one another, so the angle between them is a right angle. And of course, any vector in the 2D plane can be written as a weighted sum of u1 and u2. And you might notice that this depended in no way on the values of A and B. Right? No matter what A and B had been, we would have gotten the exact same basis coming out of this. Any questions on that? Yeah.
Would you be dividing by the length of x prime too?
Yes, thank you, x2 prime. Thank you very much. Any other questions? Okay. All right, so that's the simplest example. Now let's do something slightly more complicated that's going to illustrate or be a little bit more formal about what we're trying to do here. So for our second example, x1 is 1, 1, 0, and x2 is 1, 3, 0. Okay, so again, we can make a picture of this if we want. Well, it's a little bit harder because now we're in 3 dimensions, but we can still do it. Kind of. So here is x1, and x2 is something like this. Okay, so those are our 2 different vectors. Sorry, it's hard to draw in 3D on the board. So any thoughts on what this subspace spanned by these vectors is? Just in words, how would you describe the span of x1 and x2 in this example? Yeah, it is the horizontal plane in 3 dimensions. Okay, so we kind of expect that when we do this, we should get out 2 basis vectors that span this 2D plane, but are going to be orthogonal or orthonormal. So just like last time, we start off, the first step is the easiest one, and say u1 is just going to be x1 divided by its length. So what's the length of x1 in this case? Square root of 2. Excellent. No need to be shy. So we've got 1 over the square root of 2, 1 over the square root of 2, 0. So that is our first basis vector. And it looks just like before. It's pointed in the same direction as x1, but it's a different length. It's length 1. Okay, so there's u1. And now what we want to do is we want to define x2 prime. And we said this is going to be the difference between x2 and the, well, formally, the projection of x2 onto u1. Or another way of thinking about this is the best fit of x2 as a weighted u1. Okay, so we're going to try to represent x2 as closely as possible using only u1. How do you think we could go about doing that? Figuring out what that projection is or what that best fit is. So we've been talking about L quarter. These squares, you got it. All right. So in particular, what we're going to do is, in order to find, remember a projection, well, let's take this step by step. We could learn a weight vector W, which is the argument that minimizes the distance between x2 and the weight applied to u1. And in this case, u1 is just a vector. And so that is going to be equal to u1 transpose u1 inverse, u1 transpose x2. And that is equal to what? Yes, right, the u1s, well, they're normalized, so this is just 1. 1 inverse is 1. So we're left with just u1 transpose x2. And so now the best fit is equal to u1 times this weight, or u1 transpose x2. And this is exactly a projection matrix. This is the projection of x2 onto u1. Okay, so now what we can do is we can plug that in to our example up above. So in our example up above, we had that u1 was equal to 1 over root 2, 1 over root 2, 0, and x2 is equal to 1, 3, 0. And so what we need to compute is u1 transpose x2, and that's going to give me 1/2, 1/2, 1/2, 1/2, 0, 0. Am I doing this right? I think so. There's 1, 3, 0. And if I do that multiplication, then I have 2, 2, 0. Right? So let's just think about whether this makes sense. So our u1 vector basically has the first two elements being equal to each other and the third element being 0. x2 is 1, 3, 0. So what's the best sort of fit to that? What element that has or what vector, which has its first two elements equal to each other, is as close as possible to x2? Exactly what we derived, 2, 2, 0, right? It's as close as we're going to get if we constrain, this is as close as we're going to get to x2 if we constrain the first element and the second element to be equal one another. So now we can talk about x2 prime, which is equal to x2 minus this projection u1 transpose x2, which is equal to 1, 3, 0 minus 2, 2, 0. And we get negative 1, 1, 0. And then we normalize. u2 is equal to negative 1, 1, 0, divided by the length of x2 prime, which is again square root of 2. And so we get negative 1 over root 2, 1 over root 2, and 0. And we can even check, is u2 orthogonal to u1? Yes, if I take the inner product of this vector with this vector, it is indeed 0. And if we go back to our picture over here, and we try to draw where u2 is, yeah, it's not simple, but here's u2. It's at a right angle to u1. And together with u1 and u2, we can represent any point in the horizontal plane and nothing that goes above or below the horizontal plane. And we could even form this matrix U that we were talking about before by concatenating the columns, in which case we would have 1 over root 2, 1 over root 2, 0, negative 1 over root 2, 1 over root 2, 0. And that's our basis for this horizontal plane. Any questions so far? Okay, so that was all well and good. We only ever did 2 because things get even more tedious as you try to get more and more basis vectors. We kept things really small. Of course, if you're trying to compute this in a computer, it gets a lot easier. But now I'm going to write out the general formula or recipe. This might appear in the homework. So the input is going to be the matrix X with columns x1, x2 through xp, or a collection of vectors if you want. They're all length n, or it's a matrix that's size n by p. And the output is going to be a matrix U with columns u1, 2 through UR, or a matrix that's n by R, such that U transpose U is the identity matrix, so all of these vectors are orthonormal to one another. And the columns of U span the subspace spanned by the columns of X. So we're going to get a basis for the subspace that is represented by the columns of X. Okay, so this is our goal. And just as a reminder, R is equal to the dimension of the subspace. All right, so the first thing we're going to do is very simple. Delete any xi that's equal to a vector of all zeros. So if any of these input vectors is just all zeros, it's not going to tell us anything about what a good orthogonal basis is. It doesn't tell us about anything about the subspace at all, because any subspace contains the zero vector. So this is completely useless, and so we're just going to get rid of it. And so from now on, we can assume that any xi's that we're dealing with are not equal to 0, because we've deleted all the zeros. The second thing we're going to do to initialize is we're going to set the very first basis vector to be equal to x1 divided by the length of x1. So we're just going to normalize our very first column, and that becomes u1. I have to do a for loop, so I think I'll start over here. Now, starting with j is equal to 2, and going all the way up through all the different columns of x that are not equal to 0, we're going to do the following. So xj prime is going to be this next column, xj, that we haven't processed yet, minus the best representation we have of it using all of the basis that we've learned so far. So in particular, it is the projection of xj onto the space spanned by u1 through uj minus 1. And it corresponds exactly to this notion of a residual, or the best representation that we talked about in our two examples. And we can write that maybe in a way that you'll like better as xj minus the sum from I equals 1 to j minus 1 of uj transpose xj. So we first see how much of xj is represented by u1, pull that off. Then how much of xj is represented by u2, pull that off. And we keep pulling all these pieces off, and then we're just left with everything in xj prime that hasn't already been represented by u1 through uj minus 1. Oops, I'm sorry, this is I, where I is going from 1 to j minus 1. So we compute that xj for all the different j's. And then we set uj, our new basis vector, as xj prime divided by xj prime's length. So we normalize it. And then finally, we delete zero-valued ui's. And then that's it, we're done. So we'll use this recipe in just a second for another example where we explicitly use these formulas. But conceptually, it's the same idea as we were talking about in the earlier two examples. Only now, instead of having j only being equal to 1 and 2, j can go up to an arbitrary key. And what we do at each stage, conceptually, is what we did before. We take xj, and we see, well, what part of xj has already been represented by our basis so far? And then xj prime is just the residual, the leftovers, everything else that hasn't yet been represented. And that becomes, in normalized form, the newest basis vector. So with each new vector, we add in a little bit more to our basis. There, yeah?
So total runtime will be n to the 4th for this particular algorithm.
So the claim is that the running time of this algorithm is n to the 4th. So do you want to say how you got that?
I'm just asking. So the way I think about it is like, if you compute the ui times ui transpose will be the square root, because you call all of it since I.
Okay, so the comment is that in order to do this, I have to compute ui times ui transpose. And so if ui has got n rows, then this matrix is an n by n matrix. And therefore, I've got this big n by n matrix that I'm having to compute it every round. When you're trying to really compute these things quickly, the order in which you do things matters. So in particular, I can just put parentheses here and do this first. This inner product is much faster to compute. That gives me a scalar. Then I multiply that scalar times a vector. And so that's much faster than making this giant n by n matrix. So when it comes to actually computing this, it is important to think about the order in which you do things. Because there are multiple ways to code this equation. And as you're suggesting, some of them are faster to compute than others. Will take more running time and more memory than others. Yeah.
So then if you sum up together, will be n cubed, right?
So the question is, will summing them all together take n cubed operations? This is an order n operation. Multiplying a scalar times the length n vector is an order n operation. And then I'm going to do that j times. So that's order nj. And then I sum from j equals 110. So it's less than order n squared. Yeah. Any other questions? Yeah.
Could you explain the projection of x2 on of xj visually? Is there a way to visually see it? So
Yeah. Let me try to give it a shot. So imagine that we are in 3D space, and we already have estimated, let's say U1 and U2, and they are spanning the horizontal plane. And then I get a new vector. Now I'm working with x3. Okay, so x3 now is sort of not aligned with any coordinate, and so I want to represent as much of it as I can using these U1s. So what I do is I project it, the projection of x3 onto U1, U2. And that's going to be this point here. So this is going to tell me everything I can represent of x3 using U1 and U2. So if x3 is equal to A, B, C, then in this toy example, this is A times, so in this example, I guess what I'm doing is I'm saying U1 is equal to 1, 0, 0, and U2 is equal to 0, 1, 0. And so now my projection, or I'm sorry, x3, I can write as A times U1 plus B times U2 plus some residual. And that residual is the thing that I'm going to ultimately call x3 prime. And in this case, it is simply 0, 0, C. So in this example, my first two vectors, x1 and x2, would have both laid, I guess, in the horizontal plane. And it wasn't until I saw x3 that I got any information about the third coordinate direction. So then what I did was I said, okay, well, I can split x3 into two parts. The part that's in the horizontal plane that I've already learned is represented through x1 and x2, plus the part that's not in the horizontal plane. So this is one of the columns. This is information in one of the columns of x that's not represented in my basis so far. So now what I need to do is I need to add x3 prime into my basis, but I want it to be normalized, so I'm going to divide it by its length. Is that Kind of what you're hoping for?
Great.
Yeah, good question. Any other questions? Yeah.
The summation should be xi or xj.
In the summation, should it be xi or xj? It should. Let's just be really careful here. So we are projecting xj onto u1 through uj minus 1. So I'm summing from I equals 1 to j minus 1, and all of these should be i's. Or, oh, I see what you're saying. Yes, 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 yes. Thank you. I'm really glad you said something. This is xj. The u's are the ui's. Is that what you were getting at? Good. Thank you. Excellent point. Yes. So we're always trying to look at the projection of xj onto the u's. So we sum over each of the columns of u, but we're always projecting xj onto those columns. Any other questions? Oh, yeah.
Just another thing, I don't think we need to delete the zero value before generating the UIs. In the fourth step of the Gram-Schmidt, we need to delete the zero value vectors because the division would not compute.
Yeah, okay, so if you want to code it differently and not delete the zero valued vectors, but every time you have to divide, check and see if it's a zero valued vector, then you can do that too. It's equivalent, yeah. Any other questions? Okay. All right, so let's do another example. X is equal to negative 1, 1, 1, negative 1, 2, 2. So now I've got three vectors in a two-dimensional space, and I want to learn a basis. So what is U1 going to be? We can just use our recipe up at the top of the board over there. Okay, let me take a quick step back. What is x1? Negative 1, 1, good. What is x2? 1, negative 1, right? And x3? 2, 2. All right, so now we said in our recipe that u1 is equal to x1 divided by the length of x1. What's the length of x1? The square root of 2. And so we've got negative 1 over the square root of 2 and 1 over the square root of 2. Okay, so far so good. What's the next thing that we need to do? Any ideas? It's very hard to tell if you guys are lost or bored. I'm sorry? Yes, no, the next thing to do is to calculate U2. Very good, now you're off the hook. Okay, so maybe what we'll do, just according to our recipe, we've already done step 2, we move on to step 3. So we start with j is equal to 2. And so now we need to compute x2 prime, because once we have that, we can normalize it and we'll have u2. Okay, so it's equal to x2 minus the projection of x2 onto u1. And if we wanted to compute that projection, that is what? Anybody remember? Or see it on the board? Yeah,
U1 times U1 transpose.
excellent. U1 transpose x2. And so in this case, U1 was 1 over root 2. Wait, where's the negative? Negative 1 over root 2. 1 over root 2. And then we have U1 transpose, so negative 1 over root 2. 1 over root 2. And then x2, which, just want to get my signs right, I've got 1 and negative 1. Okay, so let's do this inner product first. So I'm going to write this as negative 1 over root 2 and 1 over root 2 times what? What is this inner product here?
Negative 2 over 2.
So I've got negative 1 over root 2 minus 1 over root 2, right? So this is negative 2 over root 2. So I've got negative 2 over root 2 times this, so I'm going to have negative 1 and 1, right? Okay, so now we can go back up here. X2 was equal to 1, negative 1. And I think I screwed a sign up somewhere. I'm sorry. Oh, yes, I did. Okay, just this multiplication. So that's negative, like that, right? Yeah, all those you guys who nodded the first time, got my eye on you, because obviously you just nod. Okay, so it sounds familiar? Yeah. Okay. So we've got x2 minus the projection, which is 1 and negative 1, which is just 0. So x2 prime is equal to 0. And now I'm realizing that we need to modify our algorithm a little bit because sometimes xj prime can be equal to 0. So sometimes if xj prime is not 0, then we're fine. But if xj prime is 0, like what happened in our example, then we're just going to set the corresponding ui or uj to 0. We've got a vector that's not really contributing anything to our basis, and at the end we're going to get rid of it. Okay, so now we've found in our little example here that x2 prime is equal to 0, and that tells us in this example that u2 is going to be equal to 0. And now we need to process our third vector. So we've processed 2 columns from x, but we still only have 1 basis vector that's not equal to 0. So now we move on to j is equal to 3, and we have to compute x3 prime, which is x3 minus the projection of x3 onto u1 and u2, but in this case u2 is 0, so we don't really have to worry about the projection onto u1. Or if we just want to be pedantic about it, we can leave the u2 in there. And so if we want to compute this, we've got x3 minus, and we can use our summation formula over there. We're going to have u1 transpose times x3, and then minus u2 transpose times x3. We just discovered that u2 is equal to 0, so we don't have to worry about this. That's just 0. And so we just have to compute this projection here. So what are we going to have? We've got 2, 2, 0 minus, try to get the signs right this time, negative 1 over root 2, 1 over root 2, negative 1 over root 2, 1 over root 2, times 2, 2, 0. Okay, so if we want to compute this inner product here, then we've got 2 times negative 1 over root 2 plus 2 times positive 1 over root 2, which gives us what? 0. Exactly. So in this case, x3 prime, or x3, which is 2, 2, 0, it's already orthogonal to all the u's that we have. So we don't have anything in x3 that's already represented by our basis so far. And so in this case, x3 prime is exactly equal to x3. So now we can compute u3, which is simply x3 prime divided by the length or the norm of x3 prime, which in this case is going to be 1 over the square root of 2, 1 over the square root of 2, 0. Oh gosh, I'm sorry guys. You were right. I got example 2 mixed in here a little bit. You are exactly right. Okay. Everything else is okay though, right? I just added in a few extra zeros there. Okay. So what?
On the what one? 2, 2, 0.
Oh, right there too. Thank you very much. Okay, yeah, we're still in the 2D space. And so now we can form our final U matrix, our basis matrix, which is U1 and U3 in this case, because U2 is just zeros. And so here we have negative 1 over root 2, 1 over root 2, 1 over root 2, 1 over root 2. And that's how you use this Gram-Schmidt orthogonalization procedure. Are there any questions? It wraps up what I wanted to say about Gram-Schmidt for now. So if you have any questions, now would be a great time to ask them. Yeah.
Would this matter if we are going from x1 to x2? This will be progressive only, right? So I can't do J3 and then J2.
Right, okay, so the question is, does it matter what order the columns of X are in, essentially? And the answer is yes. That because remember, the first thing we always do is we take the first column, X1, and normalize it, and that forms U1. And then all the columns after that are somehow defined relative to that, right? And so if I were to take the same matrix X and just shuffle the columns around, I could get totally different UIs. They still span the same space. It's still an orthonormal basis, but the actual vectors could be different, right? And you can think about it kind of like this example that we saw. Imagine we're in 3D space, and I want to just represent the horizontal plane. Well, one way to do it is to use the horizontal axis, the two horizontal axes, and call that U1 and U2. Right? That's perfectly valid. That's kind of what we saw in the first example. More or less. Another possibility would be to have 1 over root 2 and 1 over root 2, and then 1 over root 2 and negative 1 over root 2. And that's a separate set of orthonormal vectors that represent exactly the same space. And whether we get the white set or the orange set or some other set depends very much on what the very first element or the very first column of X is. So what basis vectors you actually get will depend on the order in which you process the columns. Great question. Any other questions? Yeah.
In this example, when we're only in an XY plane, what is a projection? What is the residual in that projection?
Right. So the question is, if we are in the XY plane, or just in the plane, and then we talk about a projection, what does it mean? So imagine that I've got a vector well, let's do a simple example first, where this is u1. And then I've got my new vector, x2. So the projection onto x1 is simply the projection onto that first axis. Now the same thing happens if everything's a little bit rotated. So if these are my axes and u1 was pointing in a diagonal direction, and then I come up with, but it corresponds, of course, to a subspace going infinitely far in either direction, right? And then if I've got my vector here, x2, I'm still looking for sort of this orthogonal projection. So I'm looking for the point on the orange line that's as close as possible to x2. And we said before that that's going to form a right angle with that line. So before in class we talked more about like projections of line vectors onto full 2D subspaces, but the idea for projecting onto lines is very similar. Yeah, great question. Was there another question? I thought I saw another hand. I thought I saw another hand from you. Did you have another question? No? Okay, just stretching. All right, so, well, yeah, I'll just come over here. So I said at the beginning of class that we were going to talk about 2 different ways to find these orthonormal bases. And the first one was Gram-Schmidt. It's extremely powerful. You'll notice that in order to find it, we didn't have to invert any matrices. It's not overly burdensome to compute this. So it's a great tool. But the other one that we're going to talk about is the singular value decomposition, or the SVD. And I'm going to introduce this in the context of trying to find orthogonal bases spanning subspaces corresponding to columns of X. But it's actually an extremely powerful tool that's used in many, many settings, way beyond just finding bases. We're just going to start off by thinking about it that way, but we're going to spend some time both later this week and next week talking about it in some detail because it's just so important. It shows up in so many different ways. So to start, let's compare and contrast it with Gram-Schmidt orthogonalization. Well, I'm going to say, it's going to find an orthogonal basis for the span of x1 through xp, just like Gram-Schmidt did. But unlike Gram-Schmidt, the order of the xj's won't matter. They might pop up in any order. We can reshuffle them however we want. We'll get exactly the same singular value decomposition basis vectors. And in particular, the first basis vector, u1, is the 1D subspace, or line, that best fits all the columns of X. And as we start adding on new columns, so if in particular I look at x1 through xj, this is going to be the best j-dimensional subspace, or those vectors will be a basis for the best j-dimensional subspace, fit to all the columns of X. So in contrast with the Gram-Schmidt approach, U1 through Uj, all we know about them is that they span the first j columns of X. And we don't really know anything else about them. So they tell us, so we kind of, with the Gram-Schmidt procedure, for every new j, we add in another new column corresponding to what information has not yet been represented by the next column of X. So we've got this sort of incremental approach. We incrementally add in columns. Incrementally add basis vectors with each new xj. So that's very distinct from what we're getting with the singular value decomposition, because at every step, because with the singular value decomposition, we're always trying to fit all of the data. So that can be extremely helpful for interpreting what these bases represent, and makes it easier to do all different kinds of analysis. So for instance, imagine that we have a whole bunch of data points. So each little red dot here is equal to one of my xj vectors in 2 dimensions. Okay, so I've got all these different points. So if I were to use Gram-Schmidt, then my first basis direction depends on which one of these points is somehow the first column in the matrix. But what the singular value decomposition is going to do is it's going to find the line, or the 1D subspace, that is the best fit, or in other words, closest in a squared residual or squared error sense to all of these points. Okay, so I'm going to have a unit vector, a length 1 vector in that direction, and that's going to be U1. And that's U1 no matter what order I put the columns in or what order I put the points in, because there's just one subspace, that 1D subspace, that's the best possible fit to all of these data points. And then, of course, U2 has to be orthonormal to that. So in 2D, there's not a whole lot of options. U2 is just going to be something at some right angle to it. But the singular value decomposition is going to tell us what these best subspace fits are. It's also going to give us additional information. So the singular value decomposition is not only going to tell us what U1 and U2 are, but it's also going to tell us kind of automatically that these data points are much more aligned with U1 than they're aligned with U2. And that's just going to fall right out of the singular value decomposition. Okay, so that's another way of thinking about basis representations for data points, but it's got a lot of features that are extremely useful that we don't necessarily see when we work with Gram-Schmidt orthogonalization. So the way we're going to start next time, and I want you to think about this between now and then, because it's just a starting point for understanding the SVD, is what we want to do. Let's let this vector here, or this subspace here, be A. We're going to say that our goal is to find the 1D subspace that we're going to represent as a vector A. That is the best fit, and by that I mean least squares least squares fit to the data points x1, x2 through xp. And as you might expect, things that we've talked about so far about how to compute least squares fits or how to compute projections are going to be very important. So what I want you to do is I want you to think about how you would formulate this, how you would try to write down an expression for A that'll be good. And I want to emphasize that this is slightly different than your homework problem, where you were trying to fit a line to some data. So in the homework, or in the demo that was posted by the TA, you were given points in the that were z's and y's. And if you plotted them, for instance, you might see something that looks very similar to what I'm showing there. But here, the axes mean something different. This is like my first coordinate direction x1, and this is like my second coordinate direction x2. Here, I've got features z and labels y. And so in the context of the homework, we were also trying to fit a line to the data. But the objective was a little bit different, because what we were trying to do was we were trying to minimize the distance between y and y hat. And that would always look like this. So trying to minimize the squared error in these sort of regression or classification problems is using a different way of measuring the distance between a point and the line than what we're really talking about here. Okay, so here we're trying to measure the differences between the y i's and the y hat i's. So this point here, for instance, that could be yi. And this point here, the corresponding one on the line, that's yi hat. So with the homework, you're trying to minimize the sum of the squares of yi minus yi hat. But now we're going to take a kind of slightly different view here, and we're going to say, let's just find the line so that if we were to take any one of these points and project it onto the line, that somehow those residuals between the points and their projections are as small as possible. So in that sense, here I would have a vector, let's say xj, and here this point is the projection of xj onto the subspace corresponding to A. And what we want to think about is what A is going to make the distances from these projections to the original points as small as possible. So you can still use least squares, but I want you to think carefully about it because it's also very different from the way that you use least squares in the whole. Is the distinction clear? Okay, so think about it carefully. This is going to be the fundamental building block that we're going to use to understand the SVD. The more you understand this, the easier the SVD will come to you, and we'll kick off with that first thing on Wednesday. Thanks very much.